As one of the research areas of our team under this Simon Foundation program, we are interested to explore how time-varying material can actually play a role in wave-matter interaction, and then how we can actually look at the temporal modulation, spatial modulation, and the spatiotemporal modulations of material parameters in order to have interesting phenomena in wave physics. As one of the areas of this spatiotemporal modulation, we are particularly interested recently to see how the issue of stability and instability of this type of wave phenomena can happen. In particular, we were inspired by the well-known problem of Kapitza's inverted pendulum. And about a few months ago, in June, in another meeting, a TOPIM organized by Endra in ASRC CUNY, I did talk about some of our preliminary work in that area of Kapitza-inspired, wave phenomena. Today, I'm going to talk about another angle to that problem, specifically how we can actually generalize the concept of Kapitza's inverted pendulum, and I'm going to give a brief background on that, and how we can actually bring that to other areas of wave physics. So let me see, this has to be already ready. Okay, very good. So as for the background of this topic, let me start with the well-known problem of Kapitza inverted pendulum. Many of you are familiar with that, but just for the interest of those who may be less familiar, I'm going to give you, 4 or 5 slides just as a background. So we all know, by the way, that standard, pendulum problem is a harmonic oscillator. Very familiar with the equation of that, with the small angle, of course, becomes a well-known equation, and indeed it has a resonant frequency, very well known. It is also well known that if we bring this pendulum to the other end of it, that becomes an unstable equilibrium there. And under that, of course, the equation can be modified and comes to this form. And this, of course, will give you a basically exponential variation of this for the small angle. Obviously, this is extremely well known. It turns out that back in 1908, more than a century ago, Andrew Stevenson found out that if you get actually this pendulum in the unstable equilibrium, and then you move the base of that very rapidly with a very high frequency but very small amplitude, this system becomes stable. Now, they didn't know at that time why it became stable, but it was clearly the case there. Until in 1951, Pyotr Kapitza, who later won the Nobel Prize in physics, was able to actually put this in a fantastic mathematical background and explain why this system became stable. Now, if you actually search Google, you'll see a lot of interesting videos for classes in physics from different universities. I have one of them from University of California, Irvine, that I would like to share with you to see how this thing works. So let me see, yes. So this is a pendulum that at University class of physics, they were showing University of California, Irvine. And of course, you see it's unstable. But now they start this mode of over here in the very rapid movement up and down, and system becomes stable there. Of course, it's quite fascinating that this happens there, and of course, very well known. How did Kapitza actually explain this mathematically? What he did is that he went through the Lagrangian of this system, and based on that, he was able to come to this equation of motion. And this equation of motion, of course, is very well known because of Kapitza. And you see, of course, this is the gravitational acceleration over here, and this is the term that movement of the base will give you that. But the way Kapitza solves this problem was actually quite fascinating. What he assumed is that angle theta as a function of time can be written in terms of approximation of 2 terms. One of them with the fast term, and another one with the slow term. And then when he put that in the equation, goes through a lot of mathematical steps, he was able to actually find a differential equation only on theta slow that can be written in terms of a minus of the derivative of an effective potential. But that effective potential is quite interesting. It's written like this. And if you take a look at it, you notice that this is the term that, of course, comes from the movement of this. So if you assume that the A was 0, in other words, there was no vertical movement, of course you get this potential distribution, and you clearly see at this angle, which is in the bottom, is stable, and at this angle, it's not. However, if you add that A there, then you get a dip in that thing, and that becomes stable. And in fact, yesterday, Dimitri's talk in Lagrange point got me thinking that there's got to be a connection between this and that. That we need to talk about that. That would be quite interesting connections. But that's the way, by the way, Kapitza did. And I got interested in this just recently, but very recently I decided to actually look at this problem in a very different way. Rather than looking at effective potential, I said to myself, is it interesting to actually look at this differently in order to make this more general, to see whether it would be applicable to different areas of physics and engineering. So, but before I show you what I've done, I would like to pay thanks and acknowledge two great friends. One is Vincenzo Galdi, who actually brought this very interesting paper to my attention. Vincenzo, thank you. A paper by Carlo Lizzo, that they have looked at the very interesting aspects of Kapitza there. And also another friend and the team member in Simons, Michael Weinstein, who brought this paper to my attention by his group. And that actually has a very interesting way to look at the aspects of a Schrödinger equation, that one. These two papers are very nice, and in fact really motivated me to try to generalize this concept in order to be applicable to different areas of physics. Okay, so let's go back to Kapitza's equation, motion. Of course, in general, this equation is a nonlinear equation. But for the small angle, of course, this becomes a linear equation. And then I said to myself, well, if that's the case, why don't we actually look at this very general problem? Let's actually look at a general differential equation, second order differential equation as a variable u, where u could be anything, could be time, could be space, could be other physical phenomena, which will be written like this. Now, if this k over here is constant, obviously that's a very trivial equation. If k is negative, that would give you an exponential variation. If k is positive, that gives you sinusoidal. But what if that k is a function of u itself? Now, in that case, of course, we can write it like this, let's say two terms. And let us assume, by the way, that this term, that's function of u, can be written in a very highly oscillatory way, like that. And now imagine that we look at the condition that this should be bigger than this, and this k naught could be positive or negative, and this omega should be also much larger than this. Now, under this assumption, if we go back to this equation, the question is, how do we solve this problem? Well, I mean, one way to solve this problem is use Floquet method and solve it, generally. But if we make the following assumption similar to what Kapitza did, we can actually solve this problem in a more simple, direct and simpler way. Again, just like Kapitza, let me assume that this function can be written in terms of two terms. And let's substitute that in this general equation. And as I mentioned, u could be anything, any variable. And then at this point, let's assume this condition. Let's assume that the f of fast is much smaller than f of slow. And that assumption is going to be supported as we go through this case. Now, in that case, if I take a look at this, and I look at a small variation in u, in a sense, over the period of 2 pi over capital omega, during that time, f slow is almost constant. So this derivative I can ignore. I keep this one. And because this is smaller than that, I give this one. So this equation, of course, becomes very simple for the case of f fast. And that, of course, has analytic solution that we can write it like this. And because this omega 2, I assume, is much larger than this term is small anyway. So that supports the assumption that I made at the beginning. Now let's go back and substitute that in this equation. Now we have the equation only in terms of slow. But this one, by the way, you notice that there's a very simple structure over here. The term consists of cosine omega u, and when you actually write it down, you have these 4 terms, and you have this one there. Now let's do this. Let's integrate both sides of this equation over the period of 2 pi over capital omega. And when I do that, this becomes 0, this becomes 0, this becomes 0 because this is almost constant over that period. This term does not become 0. And that 1/2 comes from here. And then that gives to this expression. This is very interesting, similar to Kapitza, but of course very general. Doesn't have to do with anything gravitation, doesn't have to do anything this. And you get like this. So you notice, essentially you get to this simple second order differential equation with the constant coefficient. And this constant coefficient is not just K naught. If K naught is negative and this term is 0, I get an expression that's exponentially varying. But even if K naught is 0, if I add this oscillatory term over here, can make this positive. And in that case, the system becomes stable. So in this case, as I mentioned, you get this one. In the case of Kapitza, that was time for angle. But this could be anything. If we write this expression, we can apply it to different parts of physics. Now, it turns out, by the way, that if I go back to Kapitza's problem that I showed you before, in some sense, Kapitza's problem was a lucky coincidence, because the term that he has over here, which is acceleration divided by L, is the second derivative of displacement. And even though displacement A is very small, but the acceleration is actually quite large in that motors that goes up and down. We don't always have that luxury in different areas of physics. For example, let's go to a very interesting, well-known case of, mass spring case. Obviously, the system is stable. Well, what if K is negative? Could we think of, mass spring constant being negative? Let's say, I don't know how to do that, but maybe my friends, Vincenzo Vitelli or Katia Bertoldi would be able to tell us how we can do it. But let's for a moment assume that if I write it like this, K would not be constant, but would be function of time, and there is a constant term over here. Now, if this term is 0, that's ordinary harmonic oscillator. And if this K naught happened to be negative, of course, that would be unstable. But even if K is negative for spring, if we add the oscillatory term of the spring, that makes it actually stable. But of course, I don't know how to make the spring constant function of time. That's number one. And I don't know how to make it actually this part negative. But even hypothetically, if such a spring is available, then that can make it positive. Unfortunately, in the case of spring, because this has to be large, I don't know of any physical quantity whose second derivative in time would be K spring. If such a quantity exists, that second derivative of that gives me a spring constant, that becomes very similar to Kapitza. But I don't know of that one. However, I know of another system that's closer to my heart, that I know how to do it, and that is LC circuits. This is also very similar to mass spring. We are all familiar with this, and of course, this is a well-known equation that we have, and of course, this is oscillatory for LC positive, and of course, we all know this. But it is possible in electrical engineering to have a scenario in which the capacitance C will be negative. That's known as non-Foster circuits. Those of you with electrical engineering interest, you're familiar with non-Foster circuit elements. So if I make a circuit in which L is positive, C is negative, by the way, as a footnote, I think 2-3 years ago in this Simon meeting, I did talk about the non-Foster circuits, so I'm not going to repeat that over here. But in order to have a capacitance negative in electrical system, we need to have an amplifier. We need to have a gain. We cannot do it with the passive structures. So that's already known, and it is possible, and people in circuit can do that. So if I make C negative and constant, and I make L positive, then of course this equation becomes like this, and that, of course, this is not a stable solution. We all know that. This is very similar to that angle of the pendulum the other side. But can I make this stable now? Now that I know how to do in electrical engineering. So I don't want to touch this C negative, but I want to actually play around with L. So can I actually have time-varying L in such a way that while C is negative, I can still make this stable? And the answer is yes. In fact, we go through the equation for the current. I don't want to bore you with the detail of that. That's straightforward, writing the circuit equations. And eventually, we get to an equation for the flux of the magnetic field in L, and we have like this. And now I'm going to use the same approach I mentioned to you in generalization. This is negative, so in the absence of this term, this will be unstable. But what if I have a time-varying system adding to that with a high value of ranging there? And how can I actually write that in terms of L as a function of time? The answer is actually simple algebra. I get from here to there, and when I do that, I get this recipe for my L to be function of time. If I change my L as a function of time in the presence of that C negative, that becomes very similar to the Kapitza's problem in an unstable and that makes it stable, and probably has some connection with the Lagrange method as well, but of course this is in time. Now, okay, so one of my postdoc who was in my group at that time, Antonio Alex, but now he's back in Spain, we did this simulation, and this is actually what you see over here. If I choose L as a function of time with this frequency of modulation in time, and there's a limit of that. If this frequency modulation is less than that limit, the system is still unstable. And you notice, by the way, this red curve is actually flux as a function of time. You notice it's unstable, but a very small variation, that is flux fast over there. But if I go above that frequency, that becomes stable there. But you might say, this is interesting, so I can change L to make it stable. But the problem is this changing in L requires L being positive, negative, positive, negative. That would defeat the purpose. I didn't want to make L negative, but I want to make it function of time. So is there any other way to do that? Yes, there is another way of doing that, and that is keep C1 negative, keep L constant, but now add another capacitor as a function of time. With a condition that C2 is a function of time, but always stay positive. And that's, of course, practically possible. You can do that. Going through a similar approach over here, if C2 is negative, obviously this is unstable because C1 is negative. And then by doing that and going through standard algebra that we do over here, we assume that the C2 is a positive quantity equal to C1 magnitude plus a little bit constant plus this time varying term. And if this condition is satisfied there, the system becomes stable. And this is the result of this. So depending on what I choose for that frequency over here, and changing C2 as a function of time, I can actually make that system stable. And by controlling that frequency, I can make the system stable and unstable. So that becomes under my control. So up to here, I was talking about circuit. But let's bring it to material. But the recipe would be very similar to that, except here, U doesn't have to be time. Could be any quantity you want. And in this case, I'm going to use U being space. So imagine now, I go back to the equation I mentioned to you before. Now U is Z, and this function is electric field component for Maxwell's equation in the medium. What does that tell us? That means, very interesting. This is a monochromatic wave. In this monochromatic wave, I have inhomogeneous distribution of epsilon. And this inhomogeneous distribution of epsilon, I can write it like this, with a constant term, which could be negative or could be positive for that frequency, plus this variation in space. This variation in space requires delta epsilon to be high and K to be large too. In that case, what does that mean, being stable and unstable? Because of course, it's a monochromatic system. But when I say stable and unstable over here, what I mean is whether the solution would be exponentially varying or oscillatory varying. So by stable and unstable, analogy will be that. So this would be the delta epsilon I want. K, of course, would be large. And then again, I follow like this. I said my distribution in space, of course, in time is sinusoidal. But in space, can I rate it in terms of these two terms, similar recipe? And I going through the algebra I showed you before, I don't want to bore you with the detail, I get a very simple differential equation with the constant term over here. Even though delta epsilon is a function of Z, very, very high oscillatory, but still for the electric field slow variation, this becomes constant. So essentially, you engineer a material with an effective epsilon. That effective epsilon, by the way, is not just epsilon r. Now, you might say, by the way, that, OK, if I take a look at this one, I have this variation in space. Average of that is 0. How come average of this is 0, but you get still an equivalent epsilon whose average is not epsilon r? That's very similar to Kapitza that he got with the acceleration there. But now we can get it in space. So let's play around with some numbers. So first of all, Shi-Shan Yin, who was in my research group, now he's at Apple, was able to actually solve this problem using a hypergeometric function. So there's an exact solution to that, but that's we put that aside. It turns out, by the way, that if you assume this alpha is 0, so you have no variation, and epsilon is negative over here, obviously you get exponential variation in z. Obvious, trivial. But now what we can do is that now we have this very interesting equation that we can design materials with, and design a very highly inhomogeneous material that will give us an effective epsilon for epsilon. And let's follow this equation. Let's play around with that. For now, I'm assuming epsilon r is negative, but I want to make this equation positive. So even though the background material has epsilon negative, and I expect to have a drop of electric field, but with putting this layer together, actually, I completely go against effective medium theory, and I showed that you can actually have a wave propagation in a background medium that epsilon is negative. So let's take a look at that. So epsilon 1 minus 1, and then I'm gonna want such that this effective thing becomes like air. So I start with epsilon negative, but I'm gonna make it like air by putting inhomogeneous material there. So let's do it. So let's say, for example, first, epsilon as a function of position is like this. The average of that is minus 1. And let's see what happens to the wave propagation over here. Okay, nothing goes through. That's not surprising, because that's like a band gap structure. But now it starts reducing the periodicity of this. Let's see what happens. If I reduce the periodicity, you notice, according to this formula, I have to have epsilon 8 to be delta epsilon to be 8. So that means this epsilon variation is between 7 and minus 9. Average of that is minus 1. So if I use the simple effective medium theory, I should still see the things dropping exponentially. But I don't. It will go through. Still messy, because still the periodicity is not short enough. Let's make it shorter. This. So this epsilon variation in space is between 39 and minus 41 with a very short periodicity. If I use just simple effective medium theory, I would expect to get minus 1. So I would expect that the wave drops. It doesn't. It will go through. This is very interesting version of Kapitza, but in material. And this has some similarity, by the way, with Carlo Rizzo's paper, but it's a completely different approach that we have there. You notice, by the way, this is E slow, and this is E fast. And you notice, as I increase this one, E fast becomes smaller and smaller. Let's look at this one. This is between 79 epsilon to minus 81. Average still minus 1. Wave goes through as though it's air. So the question is, why does this work, by the way? Because we are all familiar with homogenization. If you had given me this before I knew, Kapitza, I would have said, yeah, the average of that is minus 1, so the wave should not go through. So why is it that this works? This works because of interesting effect that happens in the magnetic field. Now, according to homogenization, if I have a very small subwavelength in homogeneity, if the wavelength of the wave is much larger than the size of the homogeneity, it has to be homogenized. That is true over here for electric field, but not for the magnetic field. Very interesting effect that happens over here. You notice that the electric field has a much longer wavelength, but the magnetic field has much shorter wavelength. Now, at first, you might say, this is very strange. Are you telling us that the magnetic field has different frequency than the electric field? No. Magnetic field has exactly the same frequency as the electric field. It appears to be faster, but it's not. In fact, if you sit at any point and look at the green curve, you notice it goes up and down exactly with the same frequency as the electric field. But the wavelength for the magnetic field is different than wavelength for the electric field. And that is the trick. And that exactly happens, by the way, in Kapitza when you look at acceleration of the angle. Acceleration of the angle is much higher. But the theta slow is what we have there. This theta plays the role of electric field. The derivative of the theta plays the role of magnetic field. And I would love to see how that connection with the Lagrange one.
You can get the Kapitza effect even with ray optics.
Exactly.
So essentially, I'm not very sure there is a connection to the electric or magnetic field.
Would be interesting to explore, yeah. I would love to do that, yeah. Okay. So this is a very interesting analogy. Kapitza's equation in Helmholtz equation. Equivalent value for the gravitational force, equivalent value for the epsilon, and so on, and split like this over there, and the magnetic field would go like this. Okay, now, it's interesting to see how this plays around in the, yes, please.
So I thought you were going to tell us in a little more physics. You told us that the magnetic field behaves weirdly.
Remember to use your seat mic, please.
In microphone, but that's okay, I can hear you.
Yep. So what is it about currents or something? What is it about magnetic part of the energy that is more sensitive to this small scale?
Excellent question. And that is because if we look at Maxwell's equation and we write the expression for the curl of H equal to epsilon dE dt, the epsilon dE dt, that epsilon has a very huge variation in space. That affects the derivative of the magnetic field in space.
So the displacement current is very weird.
Exactly. And that displacement current is proportional to the first derivative of electric field. That's very similar to the acceleration or the velocity of the angle that we see in Kapitza. Okay. So if we look at this, this basically potential curve, again, going back to this there, obviously you notice that this goes like this in a regular pendulum. If we look at the state space over here, the derivative of the angle versus the angle over here, we get the standard things over here. Now, of course, these are the stable point, and this is unstable point. Now, let's add the orientation that we have over here. You notice that, of course, is stable in that direction. This is a dip that we see there. And this is what we see over here. So this becomes stable point over here. What is the equivalent of E and H? If we do exactly the same thing in E and H, you get very similar things over here. So effectively, the magnetic field is that derivative, and electric field is what we had over here. And you see this comes right there as well. Impedance match. Because we want to actually this is like air, you notice that when I come from air to this very, very highly inhomogeneous medium, there's no reflection. And indeed, this system becomes matched with respect to that when we go to the limit of that. It's quite an unusual scenario because highly, highly inhomogeneous, and the average of that is -1, but it's still in match to air. And that's just, again, because of the magnetic field effect that we have there. Let's play around with other things. For example, what if instead of epsilon negative over here, I put 0, E and Z? In that case, I can play around with this, and I create any other epsilon I want. So I don't want to bore you with the detail. You can do it like this. We can do it. What if we start with the lossy medium? By the way, I use e to the plus j omega t convention. So this minus j means loss, plus j means gain. You notice the wave doesn't go through. But if I actually have alternate gain, loss, gain, loss, gain, loss, gain, loss over here, I can make the system lossless and go through this and fight with that epsilon lossy the beginning. That will go through. And you can start with the gain medium, and then you can make it lossless. Same thing, going backward there. And for the cavities. So imagine I have a regular cavity with the gain medium over here. This is a real part of epsilon, imaginary part of epsilon. And of course, you get the eigenfrequency that are complex with the, of course, growing term. But if I come and actually fill this cavity with the alternative value of loss and gain, loss and gain, loss and gain, very short, duration, periodicity, I get this mode of the cavity, which is stable, with the imaginary part very small. But please note again, electric field varies like this, magnetic field varies like that. Very unusual cavity field distribution that we have over here. Anyway, so moving along, so we did what we can do. But what other interesting thing we can do with this system? Can we actually have a Kapitza-inspired non-Foster metamaterial? Again, 2-3 years ago, I talked about non-Foster in this medium. We just had a paper a few months ago came out that we showed that we can have a very interesting holding and freezing electromagnetic wave and growing by creating a non-Foster system. So if I have a medium that epsilon is air, and this is one-dimensional wave propagation, this is x, and this is time, going like that. If I rapidly change the medium epsilon to 5, positive, over here, I change the frequency. And if I change it again, of course, I change the frequency, and so on. That's, of course, well known. But then suppose our theory is here. What would happen if I start with some regular medium, But rapidly, I change the medium to epsilon negative. And this epsilon negative is a non-Foster one, which means I have to have a gain. I have to have a power. I cannot do it with the passive medium. I cannot do it with the Drude material. I cannot do that. If I do that, then the frequency becomes purely imaginary, rapidly stays, froze, and then it grows. It grows, and then I rapidly change it back to 10, and basically becomes two-wave propagating both directions. That we showed theoretically there. And in that theory paper, we proposed that it could be, in the future, be implemented by having kind of like a parallel plate system with the negative capacitors over here that we switch on, switch off. And this is the simulation result with that. By the way, as an aside, Emmanuel Fort and I have a lot of discussion and collaboration to see how we can actually bring some of the concept of non-Foster from electromagnetic into the water wave and vice versa. And I'm not going to say more because he has a great talk this afternoon that is going to show how this interesting analogy between electromagnetic non-Foster and water wave non-Foster will go through. So you will see an interesting result from his group. But can we do that with this Kapitza-inspired thing? So let's go back over here. Let's come back to this expression that I showed you before. But now, take a look at this before I show you this one. If I take a look at it, this is the constant effective epsilon for a slow variation. And this delta epsilon was the magnitude of the spatial periodicity I showed you there. But you notice actually there's a frequency term over here. And of course, up to now, I was talking about monochromatic wave. But if I want to have a non-Foster with epsilon negative, I have to show that epsilon negative stays negative over a range of frequency. Obviously, this was for monochromatic. But this is a function of frequency here. Can I think of an epsilon in which it has its own frequency dependence in such a way that cancels this one? If I can do that, I can create an inhomogeneous structure whose epsilon would be negative, and at least over a range of frequency will be constant. The answer actually is right in front of us. If I use a Drude material, and I assume this collision frequency is much larger than the frequency of operation, which happens in the low frequency like in microwave, this turns out to be this. And this is exactly the formula you use, by the way, with a good conductor in microwave. And notice, by the way, now this delta epsilon has omega in the denominator. So what if I think of an inhomogeneous layer of conducting material, gain medium? Because sigma is positive and negative, positive, negative, positive, negative. Conductive, lossy, gain, positive, lossy, positive, lossy, positive, but in the form of conductive. If I do that, the sigma would be like this. I put it over here, and indeed, I can get an epsilon slow that could be negative if I choose this one larger than this, and constant over a certain range of frequency. Of course, this is an approximation. Of course, it's an approximation. I'm not saying from zero frequency to infinity. But over center range of frequency that I can use this for good material in microwave, that would be possible. So this is a very preliminary result that we have thanks to Shishan Yin that did this simulation. And so we start with a given frequency. We assume the periodicity is 10 times the wavelength over here. I mean, shorter than wavelength. And then you notice as we change the frequency, the, of course, drop would be different. But if we extract the effective epsilon out of this, you notice over a good range of frequency, this epsilon stays negative. Now, if I go to the higher frequency, this is going to drop. Because, of course, the system would not be as thin anymore compared to that. I'm very excited about this because this could be a very interesting way to actually create a material with a non-Foster system. Of course, it's a gain system because that structure has positive, negative, positive, negative, positive, negative, and negative sigma means gain. So obviously, this cannot happen in the passive medium. How much time do I have? Okay. Now, so up to now, we talk about mass spring that we didn't know how to solve. Maybe I'm going to talk to Katia to see how we can actually have a spring with that variation. Then LC circuit, we said we can do it. Then we went into metamaterial. We show how we can do it with the inhomogeneity. Then we brought it to the non-Foster system. But the beauty of electromagnetics is that we have other parameters. We use epsilon so far, but epsilon could be a tensor. So I can generalize that general equation I showed you into tensorial equation. I can also think about mu. So far, I just talked about epsilon. But what if I actually play around with mu? If I can do that, can I actually generalize the pendulum problem to the multidimensional pendulum problem? And what do I mean by that? So let's see what we mean. So let's go back, by the way, to the pendulum problem at the beginning of my talk. Of course, this was the one, that Andrew Stevenson and Kapitza did it vertically. But what would happen if I do it horizontally? Okay. That's also very well known in the literature. If I do it horizontally, I get this equation of motion. This equation of motion, by the way, is very different than that. You see there's a nonlinear function of angle over here. And of course, there's outside term. This system certainly is not stable for the pendulum being like that. But the question is it stable for other angle? So we decided to actually dig through this a little bit more. So we went back to the original pendulum problem, but this time we assumed that this base is going to move vertically and horizontally with a different amplitude, but the same frequency of motion, but maybe a phase difference between them, just to have all the parameters that we want to play around with. But the frequency of mechanical motions for these two are the same. If we do that and we follow, again, the same approach as Kapitza, we're going to get to this monstrosity equation over here, and this has an effective potential. This effective potential is this, which is generalization of what Kapitza did. Let's not worry about the detail of the mathematics of that, but we get to this point. But let's try to actually plot this effective potential to see what we see. So this is the effective potential. Let's do a few special cases. Let's assume A sub x 0. So there's no horizontal motion, only vertical motion. That's what we had for Kapitza. But now let me assume there is no vertical motion, but it's only horizontal motion. Then we get this effective potential. Let's plot both of them together. You get this one. The blue one is the one I showed you before with the stability top. But the green one also has a stability, but in these peculiar angles over here. So in other words, what does that mean? That means if I actually get the pendulum and I move it in this direction, I cannot stabilize it here, but I can stabilize it in some other angle, which can be determined by the value of that. So, and then I'm going to show you that similarly. Let's assume both of them will be there. And then, of course, we play around with the phase between two mechanical motion, and you get the whole family of this effective potential. And you notice, by the way, each one of them have different minimum point. What does that tell us? That if I can actually get the base of this pendulum and move it any direction I want with the proper phasing, I can actually make this pendulum being stabilized at any angle I want, from 0 to 360 degrees. Let's see. Let's do that. Let's start with this one. I already showed you the vertical one, so that would be boring to show. But now let me assume horizontal one. Horizontal one I start with this initial point, and then it stabilizes around here. In some sense, by the way, I can explain that intuitively because I have a gravitational force in this direction anyway, and I'm going to move this thing like this. So effectively, it creates an artificial, gravitation in that direction. So the sum of the two vectors will be in that direction, and that's what it becomes stabilized in that angle. Okay, let's play around with another angle. I start with 150 as initial point. Then I can stabilize it back there. So I can do different interesting things. And you notice, by the way, this is like this. And again, we should talk to see how interesting it is, because then you can actually change it in that waveguide system that we have there. And let's choose one more thing over here. Now you can do it at that angle you want. And you notice, by the way, the state space also follows that quite nicely. And now in the next slide, I'm going to show you an interesting video. I'm going to show you a video that I start with this pendulum. Please pay attention to this plot over here. This shows the amplitude of A sub x, horizontal motion, A sub y, vertical motion, theta, the phase between them. And then I can actually control the time any way I want. And by controlling the time, I'm going to actually make this pendulum stable around the angle I want, and I can stop at any point I want. So let's see. So take a look at this and take a look at this. Now you start this one, you're going to stabilize it over here. This is just A, then A sub y is coming to play, is going to bring it there. and then you bring the a sub x back, you let the a sub y go there, that's the Kapitzas that we had there, and then you bring back again a sub x with a different phase, you bring it like this, and then you can actually make it at any point you want. So where does this connect us to electromagnetics? What does that remind us, by the way? Polarization on the Poincare sphere. So in that sense, actually, we can come out with a series of inhomogeneous, anisotropic material that can turn any polarization to any polarization we want for the monochromatic wave we have. So that would be, let's see how much, okay. We come to, so in this case, we play around with mu. We played around with mu, but this mu is anisotropic. We have there. We go through this equation. Let's not worry about that. We use hypergeometric functions, all of those things. And you notice, by the way, that in this case, we have mu x naught, mu y naught, and then we have also term as a function of z, and with a very short periodicity and layered structure that we have there. And this would be the constant effective anisotropic mu for the field slow variation of that. And then you can start with the 45 degrees polarization coming over here, and you can end up with the polarization you want. So essentially, you can traverse, the Poincare spheres by having this. Of course, everything in space. In here, there is no time variation. There is time variation, but that's monochromatic. Let me just finish my talk by proposing follow-up ideas. We are interested in this idea. We haven't done these two slides that I'm going to tell you about. And then I have another slide for Emmanuel Forth from mechanical aspect that I would like to talk to him. We noticed, by the way, that in the case of Kapitza, he had a pendulum over here and with a gravitational force here, and he was able to actually go against the gravitational force and bring it up there. Can we do that actually in magnetism? We showed that we can do it with metamaterial. But can we do it actually with DC magnetism? For example, what if I actually pick up a compass? Just a simple compass. And if I put it in the Earth magnetic field, of course it would go that way. But that's actually also a pendulum. So if I turn this compass the other way, it's unstable equilibrium. We go back over here. But if I turn it and I add to the DC magnetic field a high-frequency magnetic field, it could be microwave there to that. So in other words, can I use this one, bring the N against the magnetic field of the Earth? This becomes an inverted pendulum, but now I add a time-varying magnetic field on that, and I can make that stable. So in other words, I can make a compass stable in the opposite direction to the Earth magnetic field. You might say, what's the use of it? I mean, so what? Okay, you can turn the compass the other way. Actually, it's interesting, because I can actually turn the compass in any direction I want, just like that pendulum I showed you. Is there an advantage of that? That actually shows us that we can do that in the magnetized material, in the magnetic domain wall. And in the magnetic domain wall, by having a DC magnetic field fixed, I don't need to change up the DC magnetic field, but I can change the polarization of the dynamic field that I can illuminate the structure, and I can make the magnetized distribution of the magnetic dipole in any direction I want. And that actually could be quite interesting from the point of view of application, because in that case, in the presence of a random noise, I can actually make sure that magnetization stays the way I want, and I actually can change it any way I want. Changing the direction of the DC magnetic field might be hard. And we can do that also probably, this is just a speculation, probably we can do that also in ferroelectric materials. If I can put a DC electric field and I actually add to that a time-varying electric field that's coming over here, which is easier to do than having DC cases, because in DC cases I have to change the electrodes, but in the wave I can just basically change the polarization of the wave, and I can make, the induced electric dipole and induced magnetic dipole in the direction I want. That remains to be seen. This is one direction. I'm interested to see how we can do it, that one. But let me also finish with just out of curiosity question, and this is particularly for my friend, Emmanuel Forth. Can I do that with the water wave, Emmanuel? And this is something I'd love to talk to you. imagine that you have a glass tube, kind of like a straw, but you put this straw, by the way, in a circular way. And imagine you put a drop of water over here, and this gravitational force is in this direction. Of course, the drop of water will come. But can I actually vibrate this glass tube left and right such a way that I can actually bring the drop of water in any way I want, in any position I want, and I keep it there? And you might ask, so what if we can do that? But if I can do that, can I actually control osmosis? In other words, can I actually create a scenario that I can move the water droplet to anywhere I want through this? Could this be useful for vegetation in order to actually bring the water higher up? If I have, motions of this, I don't know. This is just a curiosity question. So let me stop at this point, and let me thank, my co-authors that contributed to this and also other topics that we do in the Simon Foundation, some of which I presented over here. And I want to thank all of you, and particularly Andra, for putting the team together to bring all of us together. That creates a lot of interesting collaboration that I have with several of you, with Andra, with Mario, with Emmanuel Fort, with Matthias Fink, and also with some of the other guests in the audience, with Vincenzo Galdi. And hopefully we're going to have some collaboration with the Lagrange point that we have there. And so thank you all very much. I'm very excited about this because it can actually bring, some other interesting aspects of physics with this stability, and I'd be more than happy to answer any question you have. Thank you very much.